In the last video, we looked at an example of x squared minus y squared, and we computed what was called the second directional derivative using the Hessian, and we computed the second directional derivative in the direction v. And we got a positive number in this case, 2. And in this video, we're just going to dig a little bit more into this example and use it to um, as a key example of a saddle point and something that is a good example to have when we move to the second derivative test and having this example in mind. Okay, so what we're going to do here, let's make a recollection about this function x squared minus y squared. Okay, and we're particularly going to be at the point x naught y naught at 0, 0. Okay, and remember that we can compute a line. Oh, and let's pick a direction u. We can call it 1, 0, and we can also pick another direction v. We'll call it 0, 1. So we have both the x and the y directions. Okay, and remember that once you have a point and a direction, we can create a line. Okay, and that line will go through the point 0, 0, and it will point in the direction 1, 0, and then we'll multiply by t. So that leads us to the line t comma 0. If we paste that curve onto the surface, we'll get a curve r of t, so x is equal to t, y is equal to 0, and x is t and y is 0, so now there's the z entry of the curve. And we now have a curve t comma 0 comma t squared, which is essentially telling us that that x is equal to t, y is equal to 0, and z is equal to t squared. So in the y is equal to 0 plane, we have x being equal to t, z being equal to t squared, which implies that z is equal to x squared. So what we have here in the xz plane is a parabola that is opening upward because of that positive sign here. Okay. Now, you'll recall from the past what we've done is we have taken this curve on our surface and we have computed its derivative at 0. So if you take the derivative with respect to t of this as a vector valued function, and then evaluate it at t equals 0, you'll get 1, 0, comma 2t, right? And then 1, 0, 0. And this 0 right here, we knew a shortcut way to figure out what that was, okay? That you could compute the gradient of the function at the point P dot producted with the direction vector u, and that became the directional derivative in the direction u of the function f at the point P. And it was this r prime at 0 that was the direction vector of the tangent line. Okay, so what we have here is a tangent line that is flat. That's what this 0 says here. In the 1, 0 direction, the tangent line is flat. Okay, well, there is a second thing we can do here. You can compute the derivative, but two derivatives. Let's take two derivatives of the vector valued function r of t, the curve on the surface evaluated at t is equal to 0. You'll get 0, 0. The derivative of 2t is 2. Evaluating at t equals 0, and you get 0, 0, 2. And it was this 2 that we saw from before, that there was a shortcut way to compute that 2, and it was the Hessian of the function f at the point P dotted with u, dotted with u. So do the second directional derivative, and you will also get 2. And it is the second derivative, this number here, that's in the z entry of the second derivative, that tells you that this parabola, because it comes out to be 2, is a positive number, and that our curve should look like a parabola at that point that is opening upward. Okay. If you repeat this process with a different direction, try another direction. Then L of t, the curve will go through the same point, but it will point in a different direction, in this case the y direction, so we'll get 0, t. Now this tells us that our curve on our surface is x is always going to be 0, y is t, and therefore our function, because it was a function was x squared minus y squared, you'll get 0 for x, t for y, and we will get 0, t, negative t squared. Okay, and that tells us that we have in the x is equal to 0 plane, y being equal to t, z being equal to negative t squared, so z is equal to negative y squared. So in the yz plane, we have a parabola that is opening downward. Okay, and we can see that it's opening downward because we've actually figured out what the curve looks like. Okay, so we've figured out what that curve is, but we could have also figured out that it was opening downward by computing the second derivative at 0, which would have been 0, 0, negative 2. So this negative 2, the second derivative in the z entry of the second derivative of our curve on surface, okay, you can quickly compute that the Hessian at the point P dotted with V, our Hessian is 2, 0, 0, negative 2, and if we multiply that and compute the second directional derivative, 2, 0 dotted with 1, 0 is 0, 0, 2 dotted with 1, 0 is negative 2, so that's your first multiplication, and now we do a third dot product if you wish. We will get, hold on a second, have I chosen let me see, 0, 1. Oh, that's why. I was supposed to do the y direction. Sorry about that. This was 0, 1, 0, 1. We were testing a different direction. So we should get 0, 1 here. This part is correct. And then we'll get negative 2. Okay. So this tells us that this negative 2 gives us the same number as in the z entry of the second derivative at 0. And both of those numbers tell us that the quadratic approximation opens downward in that particular direction of the function. Okay. And that's what we're seeing here in this demo. We have a very important special case. This function f of x, y is equal to x squared minus y squared. If we were to look at some plots of that, we can see here that what we're seeing is the curve on the surface. So if we had a straight line in the x direction, we're seeing t, 0, t squared. We're seeing a parabola that is opening upward. But if you change direction, right there to the y direction, we're seeing a parabola that is opening downward. You've got the minus sign on the t squared. So this is going to be the key strategy for doing optimization or doing the second derivative test, is basically just figuring out if a function in any possible direction, does it always open upward? If the function always opens upward, then it's going to look like a paraboloid in that direction opening up. If the parabolas are always opening down in every direction, then it would look like a paraboloid opening down. But this function that we're looking at is a very special example. It's called a saddle point. There are functions, especially in Calc 3 class, that we have to be careful of, that some functions, sometimes they open upward, like in this direction, you can kind of go up the hill if you go in the x direction, but if you went in the y direction, you'd be heading downhill. This is an example of a saddle point, right? So we will formalize the Hessian, the second directional derivative, and we'll use this quantity to help us figure out what is going on with a certain three-dimensional function and figuring out if it looks like a paraboloid opening up or down, or does it look like a saddle point. And that would be the key to the second derivative test.